Hi, so this week is going to be a relatively big one. There's a lot of information to talk about here because we're going to talk about light's particleness in 1 week. And so we're going to talk about a couple of different ideas, which has to do with light behaving as a particle. We looked at how light behaves as a wave. Now we're going to look at how light behaves as a particle. And it kind of came from the end of the 1800s. So physicists looked back and they felt really good about what they did. Newton explained gravity, Maxwell put together electromagnetism, Thomson had started to figure out stuff with atomic particles, but then something happened. And that thing was called the Ultraviolet Catastrophe, which has to do with blackbody radiation. Blackbody radiation, what a black body is it's something that absorbs energy and then emits all that energy that it absorbs. And it kind of gets at the idea of what produces EMR, accelerating charges. So if we heat up this object and those charges accelerate, so they oscillate back and forth, they would emit EMR. Now what we would expect is as we impart greater and greater and greater amounts of energy, we would get greater and greater and greater amounts of coming off of that object. However, that's not what we saw. We saw that the frequency of EMR that was emitted dropped off in the ultraviolet range. And so that's kind of why they called it the ultraviolet catastrophe. And that was a problem. So they predicted one thing with the classical wave model, and then all of a sudden they observed something that was very different. Now Max Planck came along, and he was kind of just playing around like you would in math, like when you get a question wrong and you look in the back of a textbook and you see the number, oh, I just need to switch the sign. That's kind of what Max Planck did. He didn't really know the meaning, understand the meaning of what he was doing, but he was just kind of fixing the math. And he came up with this equation, E equals HF. And what this equation implied is that energy actually comes in packets. Energy is not carried continuously in a wave like it was thought, but energy actually comes in packets. So we actually can think about the energy in the form of light as packaged waves. And each of these packages have a certain amount of energy, and that's how it's transported. And so there's an equation for this. It allows us to find the energy of these packages, and it's equal to HF. H is Planck's constant, 6.63 times 10 to the negative 34 joules per second. There's also a value in your data sheet in electron volts, 4.14 times 10 to the negative 15. And it's really just kind of what unit we want to talk about energy in. Joules, if we try to talk about energy of a photon in joules, it's a really, really small number, whereas electron volts it's a number that's a little bit easier to work with, which is why we would do that. But anyways, the main idea is that energy comes together in quanta. So we can kind of look at this. Let's look at the smallest amount of energy from a light source that emits light at a frequency of 4.5 times 10 to the 14 hertz. So energy is equal to HF. We can do this in joules. So 6.63 times 10 to the negative 34 times 4.5 times 10 to the 14 is 2.98. 2.98 times 10 to the negative 19 joules of energy. Now, because C is equal to F lambda, we also have an equation where we can calculate the energy of a photon as hc over lambda. So we can use the wavelength instead of the frequency. Here it wants us to calculate it in electron volts, so let's do that. So I'm going to use the other Planck's constant, which is 4.14 times 10 to the negative 15 times the speed of light, 3 times 10 to the 8th, divided by 212 times 10 to the negative 9 meters. And I get 5.86 electron volts. You can see right away how this number is a little bit easier and a little less cumbersome to work with than this one, which is really, really small. If I did want to convert that into joules, well, 1 joule, 1.6 times 10 to the negative 19 joules is 1 electron volt. So I just multiply my answer by 1.6 times 10 to the negative 19. And this would be 9.37 times 10 to the negative 19 joules. So electron volts is just, it's a unit that's a little bit easier to work with. Now, Planck didn't really understand the implications of what he discovered. So it was kind of about how matter absorbed and emitted energy, because he was focusing on blackbody radiation. But Einstein actually suggested that these ideas were primarily about light itself. And so what this idea meant is that light was carrying energy like a particle would carry energy. It was being carried in packets. And so they eventually named these light particles photons. They have properties of both waves. We can see diffraction, we can see refraction, and they also have properties of particles. They carry energy in discrete chunks called quanta. So that is kind of what we're going to talk about now when we talk about light. We're going to talk about photons. There was an experiment, a famous experiment. So if we look at this, we have a charged electroscope. You see the leaves are apart. Remember, if we have an excess of charge, an excess of negative charge, it'll repel, and those leaves will be apart from each other. Well, if we shine a red laser light on that electroscope, nothing happens. However, if we shine ultraviolet light, so if we shine ultraviolet light on a positively charged plate, nothing happens. Boring. But if we shine ultraviolet light on a negatively charged electroscope, then the leaves fall. So this tells us that the ultraviolet light has some effect on the negativeness. There's negative electrons are being lost somehow because of the ultraviolet light. Now that's important to note that it has to be ultraviolet and not red light. If we think about E equals HF, red light has a lower frequency, so less energy, whereas ultraviolet light has a higher frequency, and so it has more energy. And we call this the photoelectric effect. So Einstein talked about a metal, and the photoelectric effect is we have these photons coming in, and they're hitting this metal. This metal has electrons, and we can kind of picture these electrons as being stuck in these little holes. If these electrons get hit by this light, and they don't have enough energy to get out of that hole, nothing happens. However, if this incoming light has a high enough frequency, we call that the threshold frequency, it can knock those electrons off. So if it has enough energy, those electrons can be knocked out of that hole. We call that the work function. So the work function of a material is the amount of energy needed to knock off the electrons, or to get those electrons out of the holes and knock them off that metal. Different metals hold on to electrons with different strengths. So E equals HF looks very similar to the work function of a material, which is HF, and F is just a threshold frequency. It's the minimum frequency needed to knock off electrons. We can also picture it another way, H times C over lambda. And then in this case, this would be the maximum wavelength. So what is the longest wavelength possible? That would be the least amount of energy, the longest wavelength possible that would knock off electrons. Or it could be what is the lowest frequency that would knock off electrons. So if we have a frequency of a material with a work function of 10 electron volts, so work volt is HF, the work function divided by H will be my frequency. Now this is electron volts, so we can use the 4.14 Planck's constant. So I have my work function 10 divided by 4.14 times 10 to the negative 15, and that's 202.42 times 10 to the 15 hertz. So this is the minimum amount of energy needed to knock off electrons for this metal. So this metal has electrons here. This photon that's coming in, it has to have at least this much, a frequency of that much. If it's lower than that, those electrons are going to stay in that metal. They won't be knocked off. If I have a frequency of this, then those electrons will be knocked off. Now, Millikan did this as well. He did an experiment where he shined a UV source on different metals and then measured what happened. Now, if we think about, here's a UV source, so there is a certain amount of energy coming in depending on kind of the wavelength of light that hits it. These electrons are knocked off that zinc plate. So if that frequency is too low, nothing happens. We don't get any electrons knocked off. If that frequency is high enough, those electrons come off. And if that frequency goes even higher, now those electrons come off with more energy, because energy is still conserved. This energy that's coming in has to go somewhere. So if the electron has enough energy to be knocked off and there's leftover energy, it comes off with a certain kinetic energy. So the electron travels that way between the parallel plates, and then it hits that other plate, and we can measure the current that's produced. Call that photocurrent. Now, if we want to measure the energy of the electrons, so as those electrons are knocked off, they're knocked off with a specific amount of kinetic energy. Now, as they come to this plate, we try to stop them. So we can charge this plate negatively and this plate positively. And there's going to be a change in energy of these electrons, which will be equal to the voltage required to get the kinetic energy to 0 times the charge on the electron. So our maximum kinetic energy of the electron is equal to the charge of the electron times the stopping voltage. Now, we don't always see it as kinetic energy maximum. Sometimes the question might be, how fast is that photocurrent moving? In which case we could use this equation to find out how fast those electrons are moving. So here we have determined the maximum kinetic energy of electrons emitted from a zinc surface if they are stopped by a 16 Newton per Coulomb uniform field over a distance of 3 centimeters. So here we have EK, my kinetic energy, is equal to my voltage, my stopping voltage times my charge. Now, I don't have voltage here. I'm going to have to use my other physics formula because I know that voltage is the same as my electric field times my distance times my charge will give me the kinetic energy. So this is, again, is another way to find voltage from my formula sheet. So my electric field is 16 times my distance of 3 times 10 to the negative 2 times the charge on an electron. (16 times 3). So I can do it a couple different ways. So I know the charge on an electron is 1 E. So if I want to do this in units of electron volts, I can have 0.48 electron volts. Or I can multiply my 16 times 3 times 10 to the negative 2 times the charge on an electron, 1.6 times 10 to the negative 19. And I get 7.68 times 10 to the negative 20 joules. If it's just asking for amounts of energy, electron volts are probably easiest. If it is asking us to find maybe the speed, where we're having to do some work on this side, then I'm going to have to deal with joules, because joules incorporates kilograms, meters, seconds, these quantities I need to find the speed. Okay, so the photoelectric effect. In summary, it talks about light's particleness. This incoming photon has a specific amount of energy. These electrons on the metal are in a hole. If that incoming photon has enough energy, this electron can be knocked off, and that's called the work function. Now, if the electron has more energy than's needed, then this electron comes off with a specific amount of energy. So my energy in is equal to the work function plus the kinetic energy of the electron afterwards. That's kind of the equation that we can look at and use and dealing with conservation of energy. So energy before has to equal energy after. Part of that energy goes to the work function. The rest of the energy goes to the kinetic energy of that electron. Now, if we look at that equation, so we maybe have to rearrange it. So here we have kinetic energy as a function of frequency. So my kinetic energy is equal to HF minus the work function. So our manipulated variable here is F. Our responding variable is EK. Slope controlled variable, well, I guess each one of these is a different metal, but for each line, it's the same metal. Now, if we look at this, our slope, y equals mx plus b, our slope is Planck's constant, and our y-intercept is the negative of the work function. If we think about these graphs, right, this negative, this is the minimum amount of energy needed in order for electrons to be knocked off of potassium. If it's not at that level, there's no current at all. We don't have any electrons coming off with any current at all. Now, if it is at that level, then the electrons are knocked off, and anything above, the electrons come off with an extra amount of energy. Now, there are some things kind of worth talking about. So current, when we talk about these experiments, is the amount of electrons. So if there are more electrons coming off the metal, we have more electrons. Intensity, so intensity is a word you might see. That's the amount of photons. So intensity means more photons. So if I have a higher intensity, I have more photons that are being produced. Now, intensity and current are related, but maybe not necessarily directly. In order to knock these electrons off, this incoming photon needs to have enough energy. So if I have a higher intensity, I'm going to have more photons. But if these photons do not have enough energy, if the frequency is too low, it's not going to change the amount of current. Nothing different is going to happen. If this photon does have enough energy to knock off electrons and I increase the intensity, then I'm going to get more electrons being knocked off. Because there's more photons, there will be more electrons. So there will be more current. If I increase the amount of energy, now or increase the frequency of the incoming light, I'm not going to increase the amount of current, but I'll increase the amount of energy that those electrons have when they are knocked off. So a couple of things to keep straight there. So that's the photoelectric effect. The last idea we're going to talk about is Compton scattering, which also has to do with light's particleness. So the two main things are the photoelectric effect and Compton scattering. Compton scattering has to do with X-rays being shot at metals. So we're taking these X-rays and we're shooting them at a piece of graphite. And what we're watching for is what happens when those waves actually hit that graphite. Now, if light were a wave, we would predict that the X-rays afterwards would have a smaller wavelength. However, what we find is that the X-rays after have a longer wavelength. And if you think about E is equal to hc over lambda, a longer wavelength means less energy. So there is a lower energy after that collision than before. So there's a greater energy there. We also notice that there's an electron knocked off and that they scatter at angles. So they don't just go straight through, they scatter off at different angles. Now, this has some implications. If you think back to the momentum unit, This is very similar to collisions that we looked at in the unit. So Compton found that electrons were being thrown off the target at an angle, and he was able to explain everything he was seeing, which we call the Compton effect, by using conservation of energy, the idea that light is carried in packets. So we can calculate the energy this way, E equals hf or hc over lambda, as well as the conservation of momentum. So when we see these types of questions, we can solve them some different ways. Now, if you think about momentum before and after, two-dimensional momentum conservation questions were very long. However, in a quantum type collision, remember we classified these collisions, or we said that they could be elastic. That means that my energy before, my kinetic energy before, is equal to my kinetic energy after. So these are indeed elastic collisions, which is great because kinetic energy, 1/2 mv squared, I guess that wouldn't be how I'd find it before. I'd find my energy before with just that. But the energy of the electron here, 1/2 mv squared, doesn't care about direction. So if I can use conservation of energy, it's a lot easier because I don't have to worry about vectors and conservation of momentum in 2 dimensions. So that's kind of the one thing to keep in mind when you're seeing these Compton scattering questions, is that if we can use energy, use conservation of energy because energy is a scalar and we don't need direction. Sometimes, though, we might be given momentum before and after, and we can analyze it that way. Now, going back to here, I guess if we think about momentum being conserved, so Compton found that if he did the calculations and treated it like a 2D momentum question, then numbers worked beautifully. In fact, they worked out perfectly. It's 100% conservation of momentum. And so we have this equation for Compton scattering, where the change in wavelength of the X-ray, so the X-ray before and after, is equal to h over the mass of the electron times the speed of light. And then in brackets, we have 1 minus cos theta. And theta is the angle that the X-ray is scattered at. If you Wikipedia Compton scattering, it gets in a little bit more where this equation comes from. There's some like vector things that we haven't talked about in Physics 30 that go into getting this equation, as well as Einstein relativity and other things that we haven't talked about. So I'm just going to give you the equation, but that's where that equation came from. That has some implications for light as well if we think about these these photons. So if we think about a photon traveling, a photon has no mass. So there's 0 mass to a photon. However, it does have momentum. And the momentum of a photon is related to its energy. So that's kind of another implication as well, that this massless object can actually have a momentum. We do have this equation on our data sheet where momentum is the energy of the photon divided by the speed of light, or momentum, yeah, that would be the one. So they do indeed have momentum, even though they are massless objects, which is a very particle thing. So in summary this week, photoelectric effect, Compton scattering, photons have momentum, are some implications that lead to the wave-particle duality of light, and us interpreting them as photons. So there'll be lots of different questions this week. If you do get stuck, feel free to ask. And yeah, I'll post it in the stream.